in this video we'll discuss about the flexure member and design for the timber. So I have a question here: design one of the intermediate beam of the deodar timber joist using the timber roof, and you are provided with the various data. That is, joist here is a beam, and you are provided with the spacing of joist, clear span of the joist, bearing of each joist, dead load of the roof, and imposed load, that is live load. So the very first step is to find effective length. Effective length is equal to shall be taken as the distance between the faces of supports plus half of the bearing of each joist. Okay, bearing of each joist means if this is the beam, then it will rest on support, and effective length is taken as the span, which is 2 meter. Okay, clear span of the joist. Now we have to calculate the total load acting on this member. Okay, the very first step is to calculate effective length. Second step is to calculate total load. You are provided with the dead load of the roof as 2 kilonewton per meter square. This is throughout the area. If we see in the plan, then these are the joist, and the spacing is 50 centimeter. Okay, then dead load of the roof or dead load on the beam will be given on each beam is 2 multiplied by, this is centimeter, this is meter, so 0.5 we get as 1 kilonewton per meter. Imposed load is 1.5 kilonewton per meter square, which will be distributed throughout the joist. Okay, clear spacing of the joist is taken, so it comes to be 0.75 kilonewton per meter. And self weight of the beam has to be calculated. Self weight of beam, which is given by the formula rho multiplied by the sectional area. Okay, B into D multiplied by T G by T. Assuming this is the step. Okay, assuming 200 by 400 mm square beam. Okay, this is the breadth, this is the depth. Okay, and the ratio of these two is B is equal to half by D, that is depth is twice of the breadth. So this is the assumption we make during selection of the section. 200 into 400. Now T will be cancelled out, so for rho you can see in the table. For deodar table you can find the details of the deodar. So weight of the deodar is rho is 557 kg per meter cube, and absolute this E, modulus of elasticity, is 94.8 multiplied by 10 to the power Newton per mm square is taken as Newton per mm square. 0.7 Newton per mm square, and sigma CV is 2.7 Newton per mm square. These two are written as FB and FCB in code book. Now you can calculate the value of self weight of beam, providing rho as 557 multiplied by 0.2 because it is in Newton, so 0.2 multiplied by 0.4 multiplied by 10, we get it as 445.6. it is in Newton, so providing it into kilonewton we get 0.445 kilonewton meter per meter. Therefore total load is equal to 1 plus 0.75 plus 0.445 2.1956 kilonewton per meter. Now calculate bending and for which M max is given by WL square by 8. W is the load, 2.1956 multiplied by L is effective length is 2.08 square by 8. This value comes to be multiply by 2.08 square divided by 8, 1.187 kilonewton meter. Also, we know ZP or section modulus is given by M max divided by FB. FB here is sigma B. So 1.187 into 10,000 into 1000. Okay, converting from kilonewton to Newton and meter to mm. FB we have found to be 10.2. So we get this as 11,649.8 mm cube. Now with section modulus ZP, we know the formula is BD square by 6. Then we know our assumption of B and D. Okay, this was the assumption. Now we will find the value of B and D from this. Assume D is equal to 2B, then section modulus we get the value as 116,409.8 is equal to BD square by 6. The value for D we have 2B, 55.89. Okay, nearly take this value as 60 mm. Okay, and the condition is that breadth should be greater than 50 mm or span by 50, whichever is greater. Okay, so the condition is satisfied and D will be twice of B, so it is 120 mm. Okay, now the second step, this is the first step. Okay, now for second step we have to check for shearing. Okay, check maximum shear is equal to 1 W L by 2 minus D. W is the total load acting on it, 0.1956 L by 2, effective length is 2.080 by 2 minus D is the depth which we have provided as 120, 2.195 kilonewton. Okay, and tau is equal to 1.5 times Vmax by BD, that is horizontal shear stress. Okay, so 1.5 times 2.195 BD. B is the width, which is 60 into 120, get 0.45, which should be less than the value we have taken for the from the table, so less than tau u. Okay, this is okay, this was the permissible value. Third step is check for bearing. Okay, check for bearing. Bearing reaction or bearing force, we can say bearing force is given by WL by 2. W is 2.1956 multiplied by effective length, that is 2.080 by 2, 2.28 kilonewton. Now bearing stress is given by bearing force by width multiplied by support width. okay, and bearing force here is 2.28 into 1000. B is the value of B is the width 60, and support width is the depth for which the member or beam is resting. Okay. So support width is equal to bearing of each joist. Okay, support width is bearing of each joist. So we get this value as 0.475, and it should be less than sigma CB. Okay. Now check for deflection. You have to make check for deflection. That is the fourth step. Check for deflection. Deflection calculated is given by, we see 5WL4 by 384 EI. Okay, W is the load, L is the length, effective length, 384, E is the elasticity which we have found from the table, 94.8 into 10 to the power 2, and I is the moment of inertia as BD cube by 12. So 60 into 120 to the cube by 12, we get this value. Finally we get this as 0.66 mm. Okay, and for delta permissible it is S by 240, S is the span, and 8.66 mm, which is greater than the calculated deflection. So deflection check is okay. So in this way the checks for various components has been done. So you can provide a column, provide a beam of 60 into 120.